Thanks for the wording. Okay, so the third axiom is just that this thing is equal to, well, okay, I'm just going to do it. Okay, because this is a little different than the 250B case. So what we do is we just put down the formula, 3ax plus by plus 2cz. And then what you do is you just literally like put a bar on top of all that, right? And that is a safe thing to do because everything's real. So the conjugate of something that's totally real is still real. And now you just really want to imagine, well, maybe I should just put the x's in front of the a's and the y in front of the b and the z in front of the c. So this is just the conjugate of the inner product of ABC with XYZ. I'm sorry, I got it backwards. And XYZ with ABC. Right. But that bar really is pretty well meaningless.
Yeah, so we can take that bar away because it's real numbers.
Yeah, I mean, basically this step would be since 3ax plus by plus 2cz is already real anyway. So that would be a safe thing to do. Okay? Okay, and then can somebody remind me about the fourth axiom? That's the one?
The inner product something but with itself is greater than 0 unless it's 0.
Right, so this should be at least 0, right? The formula for it is just basically 3a squared plus b squared plus 2c squared. And that is certainly greater than or equal to 0 since a, b, and c are real. And it is equal to 0 only if a equals b equals c equals 0. Okay, so that was a fair bit of work. That's good to practice. I might ask you to show that something's an inner product. I may not ask you to show all the axiom. I might give you a choice. Say, verify your favorite parts of it, and whatever. But I won't ask you to remember them in order. I won't say verify axioms 1 and 3. I wouldn't do that. I'll either explicitly write out what I want you to check, or I'll just say list your 2 favorite axioms and check them. Okay, so it won't be. The exam will not be tied to the book, in the sense of knowing what result was numbered what or listed in what order or anything like that. I don't believe in writing things in that format. So, okay, so that was part A, but that wasn't really the part I was trying to get to. Good to practice it. But what I want to do now is get on to part B. I want to define a transformation T from V to V via T of ABC equals 5A minus C, comma, 2B plus C, comma, negative 3A. I suppose I could ask you to prove that that's linear, but let's just assume it for now. So technically you'd have to check that that does respect addition and scalar multiplication. But it would be pretty easy to do it. Actually, let's talk about that for a second. There's an easy way and a hard way to show that this is linear. The hard way is show that it respects addition directly and show that it respects scalar multiplication directly. Does anybody know a fast way to check that this is linear?
Oh, don't we already know that linear is going from V to V?
No, that just means it's a linear operator.
Oh.
Once we show that it's linear. Christine?
Is there some way you can combine them somehow? CX plus Y, for example?
Cx plus
Yeah,
y.
well, it'd be, in this case, it'd be.
It just means do both of them at the same time.
Both of what?
So if we had T of X, we could take T
Sorry,
of CX.
both of what, Christine?
Like the combine addition and scalar multiplication.
Oh, showing them together. Well, oh, I see. The 2 parts of showing. Yeah, you can do that. Okay, that's still the hard way.
Isn't it like the standard basis spans that one? That would work too?
Standard basis spans V.
Oh,
I don't know what you mean by spans that one.
the right side of it.
That's not what I'm looking for. Anybody know what I'm looking for? Nobody knows.
You say Dr. Gannon assumes that all things are linear.
There you go. Let me write it like this. Does it start to look a little familiar?
Oh, it's the ranked something.
No, my point is just this, that this transformation is a matrix transformation, right? It's defined by a 3 by 3 matrix. Capital A being this matrix here. Anytime you have a matrix transformation, it is always linear. We could check that. You know, Tia and here, just to make Christine happy, we'll check both addition and scalar multiplication at once, right? Kind of combine them into one thing. So it's linear, right? Basically, you just get capital A times Cx plus y, right? And then you can pull the C out, get A times x plus A times y, and that's just C times T of x plus T of y, right? So it's very easy to show that all matrix transformations are linear in one breath, one time in your life, and then every time that the matrix changes in the future, you don't have to reprove anything. You just go straight to here. Or you just quote this fact, that this kind of transformation is always linear. It's because you're going, anytime your transformation is going from Rn to Rm, any linear transformation, guys, this is a very important fact. People at the end of 307 should know this. Anytime you have a linear transformation from Rn to Rm, it must be of this form with an M by N matrix, capital A, sort of defining the transformation. There are no others, is what I'm saying. So I'm saying more than what this says. This says that transformation is linear. I'm saying even more than that, I'm saying it's the only thing that's linear when you're going from Rn to Rm. Which is actually powerful because we also proved at some point this semester that every n-dimensional vector space is isomorphic to Rn. So actually, if you have any transformation from V to W, you can essentially view it as a transformation, assuming that they're both finite dimensional, you can essentially view any linear transformation from V to W as a transformation from Rn to Rm, which means it can be put into this form where there is some matrix there. But then again, that shouldn't surprise us either, because anytime you have a linear transformation, there's always a special matrix that we can associate with it, which is the matrix representation. So
does that mean everything that we do is going to be linear?
no, just everything of this form here, like this would be. So everything of this form is linear, right? And anything that's linear has to have this form.
Yeah.
But there could be nonlinear things out there. If there were no nonlinear things out there, then Math 307 would be the only math class there was, because everything's linear. Good stuff.
So on the exam, it's like you unspecify that piece when B is linear. Do we have to put it in that form to use the linear property?
You don't have to rewrite it like this form, but I will either tell you that it's linear or I will ask you to explain why it's linear. I'm not going to leave it open-ended, so you'll know what you're being expected to do. Yeah, so actually, basically, you guys know what this matrix is, don't you? This matrix is just that. Right? What's T of 1, 0, 0? Well, T of 1, 0, 0 is 5, 0, negative 3. That's the first column. Okay? and so on and so forth. So it's not that surprising. We're basically just, again, emphasizing that this is a transformation, so there's of course a matrix associated with it. Matrix representation. I still have not gotten to my question. Yeah?
So branching off of this, is that saying that if T was not linear, then there would be no way to write a matrix?
Right, that's true.
So
Because if you can write a matrix for your transformation, this proves that it is linear,
how would you not,
contrapositive format.
how would you not be able to write a matrix?
How would you not be able to write a matrix? Well, what if I did something like, I don't know that. That's not linear. And I don't know how you're gonna deal with that. I mean, you can't just put a squared here, because then this part doesn't work. I mean, there's just no way to do it.
Oh, so pretty much just if it has just,
It's basically gotta look like linear equations.
okay. And if it, okay.
Okay, so ready for the question. Finally ready to ask my question now. My question is, find T star of 1, 1, 1. The adjoint of 1, 1, 1 under this transformation. Okay. So, does anybody know how I'm going to want to do that?
So first name,
Richard? A matrix representation. I like that idea. So we would like to do a matrix representation of T star. Okay.
we already know it.
So we want to do a matrix representation of T star with respect to what basis? Standard? I'm disappointed? I wasn't trying to look disappointed. I was trying to give you a moment's thought to see if you really want to use the standard basis.
Why wouldn't we?
What kind of basis do you have to have here in order to do the matrix deal with the T star? Orthonormals. Is the standard basis orthonormal?
No.
So the standard basis would be 1, 0, 0, 0, 1, 0, and 0, 0, 1. My question is that an orthonormal basis?
Yes, because only like one. No, wait, no. You have to divide by roots of 3. You have to divide by roots of 3.
The correct answer to my question, is it an orthonormal basis, is it all depends on the inner product. If I use a standard inner product, then the answer is yes. But you see, I'm not using the standard inner product. Admittedly, this was like 20 minutes ago. But this is the inner product. So the inner product of 1, 0, 0 with 1, 0, 0 is 3, not 1. So the length of the vector, so I don't want to use the standard basis. The length of the vector 1, 0, 0 is actually the square root of 3. Remember, it's the square root of the inner product of the vector with itself. The length of the vector 0, 1, 0, well, that one's just 1. Square root of 1, which is 1. And what is the length of the vector 0, 0, 1? Square root of 2, right? It's the square root of 2. So we do not have unit vectors. Now, the other issue is, are they perpendicular to one another? Because if they're not perpendicular, then they're not orthogonal either. So is 1, 0, 0 perpendicular to 0, 1, 0? How do you tell? 1, 0, 0 with 0, 1, 0. Do you get 0? Okay. What about 1, 0, 0 and 0, 0, 1? Okay, and what about, I gotta do all pairs, right? I gotta check every possible pair of bases. What about 0, 1, 0 with 0, 0, 1? Are you all seeing that? Is everybody seeing that? The standard basis is orthogonal. It's just not orthonormal. So what we're going to do, and this is one thing everybody needs to know, instead of using the standard basis, what I'm going to do is I'm going to replace it with an orthonormal basis. How do I take vectors that are orthogonal and make them orthonormal? Right, divide by the magnitude. So I'm going to use 1 over radical 3 times 1, 0, 0. And then 0, 1, 0. And then 1 over radical 2 times 0, 0, 1. So that Make some sense? So it gets messy. These problems get a little bit messy. But now we can, if we are willing to do that, then we can use Richard's approach, which is that using that basis, the matrix representation of T star, according to theorem 6.10, that basis is the matrix representation of T with respect to beta conjugate transpose. Right? So I need to find, I need to find the matrix representation. Let me just put my conjugate transpose there. And then I'm going to build this matrix T sub beta. And how do I do that? Well, I take my basis vectors, I transform them according to this equation, and then I write the answers again in terms of this basis again. So you have to do this very carefully. So I'm going to transform 1 over radical 3 times 1, 0, 0. Using this definition. So what am I going to get? I'm going to get 5 over radical 3, right, comma, 0, comma, negative 3 over radical 3, right? Now, here's the thing, please do not make this mistake. These 3 numbers do not go in this column yet. You have to take these 3 numbers and write them, you have to write this vector back in terms of this basis again, right? So in other words, I would argue that this is 5 times the first basis vector, right? And then plus 0 times the second basis vector. And then, plus something times 1 over radical 2, 0, 0, 1. So I have to figure out what scalar do I have to put right here so that I'll end up with negative 3 over radical 3. Well, the answer is you put negative 3 over radical 3 there times radical 2. Actually, radical 3 divides into 3 and leaves you with radical 3. So this is actually, just if you want to make your high school teachers happy, this simplifies to negative radical 6.
Yes.
Okay, so what are my scalars? 5, 0, and negative radical 6. Okay? 5, 0, and negative radical 6. Is everybody okay with that? Okay? Let's do T of the second vector in my basis beta. T of 0, 1, 0. What is that going to give me?
Just 0, 2, 0.
0, 2, 0, right? Would you agree that that's just 2 times the middle vector again?
Oh,
So when I put down the second column, it's not so bad. It's just 0, 2, and 0. Just like that. And then I got to do T of 0, 0, 1. I'm sorry. T of 1 over radical 2 times 0, 0, 1. 1 over radical 2, 0, 0, 1. Okay? So that's going to be negative of the C entry, so negative 1 over radical 2, comma, 1 over radical 2, comma, 0, if I did it right. And I now have to write that back in terms of beta again. I have to write that back in terms of beta again. So, let's see. I'm going to have 1 over radical 3 times 1, 0, 0. Times what scalar do I need in order to get negative 1 over radical 2? Negative radical 3 over radical 2, right? Okay. Plus, my next scalar is 1 over radical 2 times 0, 1, 0. And then my last one is just 0. So my scalars are negative radical 3 halves, then 1 over radical 2, and then 0. And now I have to conjugate transpose that. That's the easy part. But I conjugate transpose that. The first row becomes the first column. negative square root here. First row becomes the first column, second row becomes the second column, and the third row becomes the third. Okay. I'm gonna get rid of this. Those of you guys coming in late, this is all being videotaped, so you can look back at it later. We're doing a problem that's actually not on the review sheet. I'm practicing stuff in 6.3. Basically, we are given a transformation from R3 to itself, and we are trying to find the adjoint of 1, 1, 1. Okay, so I have a matrix representation for T star. So that's helpful, but of course I'm not done yet because I need to find T star of 1, 1, 1. So how do I evaluate this using the matrix? Do you remember how to do that? This is good practice with that. So I'm going to take this matrix and multiply it on the right by what? Please don't say 1, 1, 1. Because that would only be right if it was the standard basis. I have to take 1, 1, 1 and write it in terms of this basis, right? In other words, I have to find the coordinate vector for 1, 1, 1 relative to this basis. Again, why am I using this basis? Because I have to have an orthonormal basis for the vector space. Okay, so I'm going to take 5, 0, negative radical 6, 0, 2, 0, and negative radical 3 halves, 1 over radical 2, and 0, and I'm going to multiply it by some column vector, but I have to figure out what's the right column vector to use here. So I have to take 1, 1, 1 and write it in terms of this basis. Would you agree that it is the square root of 3 times this vector, plus 1 times this vector, plus the square root of 2 times this vector? So then that's my coordinate vector. Square root of 3, 1, square root of 2. So I have to put those guys in there. Right, so this is the coordinate vector. This is 1, 1, 1 relative to beta. So 1, 1, 1 relative to beta gives me that. Yeah. So 1, 1 is radical 3 times 1 over radical 3, 1, 1, 0, 0, plus 1 times 0, 1, 0, plus radical 2 times 1 over radical 2, 0, 1, 0, 1. Making sense? Okay. So now we're going to just do this. So what we have here, guys, all we have right here, this is just simply T star with respect to beta times our vector V with respect to beta. This being our vector V right here. This is V. Okay? So we're going to do this matrix multiplication. We're going to get something kind of messy. 5 radical 3 minus radical 12. And that does simplify. 2, and then negative 3 over radical 2 plus 1 over radical 2. And that actually simplifies to 3 radical 3, 2, and negative radical 2. Okay? Everybody with me? See, radical 12 is the same as 2 radical 3. So I have 5 radical 3 minus 2 radical 3. That leaves me with 3 radical 3. The second entry is easy. The third entry, this is negative 3 over radical 2 plus 1 over radical 2. That's just negative 2 over radical 2, which is negative radical 2. What this is here, guys, what this is here, this is T star of V. This is what we want, except it's a coordinate vector for it. It's the coordinate vector for it. So you have to remember, what does a coordinate vector mean? It means the actual vector, T star of 1, 1, 1, the actual vector is just literally this number times the first basis vector, plus this number times the second basis vector, plus this number times the third basis vector. So let's just write it down. 3 radical 3 times 1 over radical 3 times 1, 0, 0. So you can see that that's just gonna give you a 3 in the first slot. And then plus 2 times the second basis vector, which is 0, 1, 0. And then minus radical 2 times the third basis vector, which was 1 over radical 2 times 0, 0, 1. Okay, so this actually ends up giving you 3, 2, negative 1. And that is the final answer. It's actually not as bad as, I make this all look to be. We're just kind of going through it slowly. But it's not that bad. Everybody following this? This is like the group work number 8 problem. Or the group work number 8, that second problem that we didn't really fully finish. Just to make sure we're really getting that, let's just try something real quick. What if I do, because we know what the formula is for the adjoint. What if I do t of any point inner product with 1, 1, 1? It should be equal to the inner product of x, y, z with whatever we just said t star of 1, 1, 1 is, right? This is the property of the adjoint. So this should be true. Let's see if it is. Let's do the top line and then let's do the bottom line. So on the top, first of all, what is t of x, y, z? Actually, instead of x, y, z, can I call it ABC?
Yes,
Let's just change these to ABCs. I'm so sorry. ABC. I was not thinking ahead very well there. Choose ABC. So this guy is literally just the inner product of this one with 1, 1, 1. But we're using the inner product that I gave you originally, not the standard inner product. So it's got to be 3 times this. So 3 times 5a minus c plus this one times this one, so 2b plus c, plus 2 times this one times this one, so minus 6a. To go back to the original inner product that I gave you, the original inner product, which was over there originally, was 3ax plus by plus 2cz. I gave you a non-standard inner product, which is why this whole problem became messy. Right? Now how about doing this one? Well, t star of 1, 1, 1, if we did it right, the answer was 3, 2, negative 1. So let's do the inner product here. It's 3 times a times 3, 9a, plus b times 2, plus 2 times c times negative 1, so that's minus 2c. Please tell me those are the same. If they're not, we have to go back and start the whole thing over again. I don't think anybody wants to do that. Yeah, these are the same. These are the same. So at least this does work. This is just confirming it. This is just confirming the all-important equation right here. Okay, does that make sense? Okay, great. So I guess, how do you feel about that? So, well, okay, let me ask you another question. Would you like me to go over that problem from the group work 8 kind of in, or maybe I could give you the sort of a faster version of it. Or do you want to just read that one on your own? It's kind of similar to this one, but it's got these messy radicals in it as well. It's only got 2 dimensions, so you're only dealing with 2 vectors. Your matrices are 2 by 2. Yes? No? Want to see? You're okay with it? So just basically, it's another. I just made up this example because what I was figuring was that everybody's already read the group work solution, and then this was just going to be another one to show you in addition. Yeah, Christine.
The group work solution, are we given a different inner product?
Yeah, it's actually polynomials. That's a polynomial example, and instead of the basis 1 and x, you'd have to take those